Hey guys, welcome back to another episode of Will It Fail? So you new viewers who do not know what a Will It Fail video is, it's a video where I test specific components or a component of a system. And we kind of stress test them to see if they'll break or if they can handle the rated current or whatever the test is. So today we're going to be digging into the Yixiang version 1 components, specifically the circuit breaker and the 50mm cable that runs from the circuit breaker to the JK inverter BMS. And we're also going to be testing a couple of the different stud types. We're going to test the double M6 stud, and we're going to test the single welded style stud. They're both welded, but one's got the two M6 bolts, and the other one's just the single welded stud. We're going to push about 200 amps through those, and we're going to compare the heat on each stud and the bus bars to see if one is more efficient or better at transferring current than the other. Yeah, so a couple of you mentioned that the 50mm cable going from the breaker to the BMS cannot handle 200 amps continuously. A 48 volt battery at 200 amps, that's 10,000 watts. That's a lot of power. I don't know who's using a single battery with 10,000 watts continuously. But that's what they say and claim that it's rated for. So I figured, let's try it out. Let's see if it can actually do it. So let's take a look at the test setup. Okay, what we have here is 4 cells wired in series to create a 12 volt pack. The reason why we're doing this is because with the 48 volt battery, it's very difficult to pull 200 amps. As I just mentioned, that would be 10,000 watts. I don't have a way to draw 10,000 watts. Very easy to do with a 12 volt pack. You only need about 3,000 watts. We have these wired without a BMS. We're just going to raw dog it because all we need to do is produce enough current to be able to heat up this breaker and trip the breaker and heat up this cable and see how hot it gets. So the max we'll probably run the test for is about 10 minutes. That should be enough. We'll just monitor the heat. If it does not continue to get hotter, then this test will be done. Okay, so looking at the breaker, you'll notice that this is a 220 amp breaker, continuous rated. And on the side there it says 275 amp trip. So that's what is required to trip the breaker, it's 275 amps. Now, if you look closely, you'll see this little bridge piece, this little metal bar. See that sitting underneath the terminals of the breaker? It actually has it on both sides here. You can see it there. Now, it doesn't make sense that they have it on this side because this bus bar has 2 holes on it, so it can span the breaker by itself. So it's very strange that they have this little piece of metal inside there between the contact terminals of the breaker and the actual bus bar. And this is how it is exactly in the box. I have the same setup going on. I didn't want to remove any pieces or parts. I wanted a close simulation of how it behaves in the box. So I'm not quite sure why they have that on this side. On this side, they used a single lug, a single hole lug on this side, and over here on the BMS side, this would normally be on the BMS, it has an actual double hole lug over here. And this is something I complained about when I did the review video, is why they didn't use a double hole stud or lug on both sides of this cable and just span the 2 contacts and get rid of this little piece in the middle, because this is, if you notice, it's quite thin and it's basically obstructing the current flow. There's no need for this. I mean, they have it here obviously so it can span the 2 poles and act as a bridge, but totally not needed if they used a double hole lug, and definitely not needed on this side. So we're going to do 2 tests. We're going to do 1 test with these in, how it is from the factory, these little metal spanner bars. And then we're going to remove them and see if it runs any cooler. We'll flip this cable around. We'll have the single lug over here on the inverter, and we'll have the double lug over here directly on the contacts of the breaker and will remove this little piece of metal. Now, I'm no electrical engineer, but to me that looks like it's just inhibiting the current flow. So, but what do I know? On with the testing. But it really doesn't matter anymore unless you own one of these boxes. I have 2 of them myself because they don't sell these anymore. They sell the version 2, which comes with a nice beefy bidirectional circuit breaker. We'll be reviewing that in the next video. Now, on with the testing. Okay, so before we start the factory test, let's do a baseline ambient temp check. So we're looking about 70 degrees on our battery pack. Breakers at 73, inverters at 74, and the room temp is about 72, it looks like. Got the clamp meter on the 50mm cable here. We're going to push about 200 amps. $96 right now, 97. Okay, we're pushing 202 amps right now. These terminals are already quite warm. Oof, yeah. Those are warm. But the cable is actually pretty cool to the touch. The terminals are definitely hot. So these are the double stud terminals, sitting at about 130 degrees. Inverter fan turned on, 170 degrees on the stud there. Anyway, let's check the breaker. Breaker's at 130 near the contact. But the cable is doing pretty good. 106 degrees. I'd say the main problem right now is the studs themselves. The bus bars. 180 degrees. Let's check the lug on the cable. I do not see a problem so far with the breaker or the cable. Contact terminal on the breaker about 110. The breaker itself internally 130. That's the hottest point right there, 132 degrees on the breaker itself. The cable's good. I do not see a problem with this cable at all. I'm still pushing 200 amps. It's been about 5 minutes. Okay, so the fan's kind of blowing on the breaker here. We don't want the fan to be cooling that down. We just want... Can't have anything affecting the test here. We're pushing up on 8 minutes now. And the terminals on the breaker are, yeah, they're hot to the touch. You can touch them for maybe ooh, not that one. A couple seconds there. Let's check our temps. Still pushing 200 amps on the meter there. Let's check our battery cable. So it has increased about 30 degrees up to about 130 degrees on the cable itself. It's not as hot as the bus bars. These bus bars and the studs still 160, 170 degrees. That one I saw 180 a minute ago. Let's check the terminal on the breaker. So the breaker's gotten up to 160 degrees. That's pretty warm. I don't like anything to be over 140 degrees. But it hasn't tripped. We're running about 90% duty cycle on this breaker. We're almost 10 minutes. Our cable is still sitting at 130 degrees. So I'm pretty impressed with the cable. Alright, so there's 10 minutes, and I think everything's sort of leveled off, where it's not really going to heat up anymore, given our ambient temp. Look at that bus bar, wow, 192. That's a little hot for the bus bars, that definitely is too hot. I'd be more concerned with those than anything. Let's go ahead and boost it up, and we'll make sure the breaker trips at or around 220 amps. We're going to boost everything up. Here we go. $300 amps. Oh, the inverter cut out. Inverter couldn't do it. Let's reset. Okay, here we go. There, 250 amps. It's got a trip rating of 275 amps. This thing's putting out some heat. It's making me nervous, especially them bus bars. There it goes, it tripped. Alright, so we did get a trip on the breaker. So the breaker does function as intended. Alright, that concludes our the first test. Let's check the heat. So we'll compare once we take out those metal shims, see if we can't reduce the temps in the breaker. Okay, so the breaker did work as expected, so I'm happy with that. The terminals did get warm. That's pretty normal for those kind of breakers. They will get warm around the contacts. But 160 degrees, that's a little too high. I like to see things below 140 degrees. The 50mm cable did fine. The lugs got warm because they're in contact with the breaker contacts. But the cable itself never got above 130 degrees, so that's below 140 degrees. So I think the cable is sufficient. I mean, if you want to scrutinize anything, it's definitely the bus bars. We see near 200 degrees, that's crazy. Which I'm kind of surprised, especially with the double studs having those large surface areas to mate with the bus bars. I'm surprised it got that hot. So I just realized something. I was using the aluminum bus bars. Okay, so the original Yixiang box I got, they sent me two different bus bar types. They sent me these rigid ones right here, the ones that I'm using now. These are aluminum. These came with the cells, and the actual box comes with these copper flexible bus bars. You can see the copper there, and this one is just silver. So if you do end up getting the Yixiang box, make sure you use the copper flexible bus bars. As far as I know, they do not ship the aluminum rigid bus bars anymore, but if you end up getting both, make sure you use the copper only. We're going to rebuild this battery pack using the flexible copper bus bars, and we're going to take these metal bridge pieces out of the breaker. Everything's been reconfigured. Let's check it out. We have flexible bus bars on all our battery connections. On the breaker, I removed the two bridge pieces of metal, so it's direct contact with the bus bar here. I flipped the cable around, the 50mm cable. The single hole lug is on the BMS side, or the inverter side, and the double hole lug is on the breaker side in direct contact with the breaker itself. So no more metal plates. Okay, here we go. Modified setup with copper bus bars. Let's hit it with 200 amps. Here we go. 211 amps. Start our timer. The first check-in will be at 2 minutes. Can't have the fan in the way. We're approaching 2 minutes. Let's take our first heat reading. First, we'll check the bus bars. Looks like about a max temp. I can't read that red. It's 130, and our target is 100. 130 on the bus bar. $195 on that one. That's crazy on the max. That bus bar, if you look back, look at that. That particular bus bar. You can see over the whole pack, that one is definitely hotter. Let's take a look at the breaker. The breaker's actually looking pretty good. Cable is only 105, 111 max right there, 112. The actual terminal, just 110 on the terminal. Sorry, last time it was 160 is what it got up to. Yeah, 160 is what we're trying to beat here. You can see right there though, 168, just like last time. The internals on the breaker itself. Wow, look at that internal temp. That is crazy. That is right here. Yeah, that's warm. Still pushing 200 degrees on that bus bar. Wow. Same there. That's consistent. That's 140 degrees on that one. But you go to this one and look at that. Wow. 160 on the target with a max of 202. What is up with that one? Let's take a look at our entire pack again. Yeah, that bus bar. That one right there. Look at that thing. Let's take a look at our breaker again. We're at 7 minutes, 40 seconds. The side of the breaker there is 150 degrees. But as far as the contact terminal goes, it looked like a significant improvement there. I can just see the color profile there. You can see the lug, the double lug right here. This is pretty cool. You can touch that, no problem. Just about 90, about 100 degrees right there. Let's check out our cable. Same thing, 130 degrees. That's what we got last time. Doesn't seem to be going over that. Look at that breaker. It's like one of those fire blocks in Minecraft. So we are over 10 minutes now. Seems like everything's maxed out. Nothing's climbing anymore. We're sitting at 200 still on that bus bar. I think average we're pulling about 150 degrees on the bus bars. Let's pop the breaker. Turn it up to 250 amps. See if we can pop the breaker. Takes about 30 seconds at this rate. Makes me nervous. We're pushing these cells at about 1 C rate. These are 280 amp hour cells. We're pushing 250 amps. There it goes. So the breaker's still working. Alright, so I pulled out the old Ducon cells. They've been sitting around for about 2 years. So I was thinking last night, and I was thinking about that one bus bar that was really hot. I was like, what could cause that? Because the other bus bars were 50 degrees cooler. It could be due to that one cell having a voltage sag. So if we see that again on these, well, maybe we'll do some more testing and actually check the voltages while we're doing the test of each cell. Okay, so same as before, except we're using the single welded stud cells. We're using the flexible bus bars, and I have the 2 metal shims removed from the breaker. Okay, let's do an ambient temperature check. 70 degrees on the batteries, breaker, inverter, and we're sitting at 72 in the room on the thermometer up there on the wall. Okay, let's go. Right, what the hell is that buzzing? The inverter? Jesus. Okay, we're coming up on 2 minutes. We're gonna do our check here. I'm doing the overlay mode so we can kind of see what we're looking at. So I'll just do an overview here. Looks like those bus bar on the breaker is the hottest. 113. About 102 there. 102 on that one. That one's surprisingly cool. About 100 degrees though. Same with that one, about 100 degrees. It's actually 5 minutes already. I'm trying to keep this short so I don't... The video is already getting too long. So we're just going to come back in 10 minutes. We'll skip the 5-minute check. At 6 minutes in, I could not do this on the other cells. That is really interesting, actually. Let's check the voltage. Yeah, right around 12 volts, so we're still good. Three volts on the cell voltages. Coming up on 10 minutes. Okay, we're gonna do our 10-minute check here. It's 10 minutes, 30 seconds so far. So looking at the entire pack, we still got the bus bar on the breaker is still the hottest. Let's look at the individual bus bars. 100 degrees on that one. Okay, we're at 140 on that one. That's the one that's that's connecting the breaker. 100 degrees on that one. And 100 degrees on this one. They're all consistent. Every bus bar in the pack said for this one, because of the breaker, is at 100 degrees or less. That is nuts. What is going on here? So we're seeing the similar temps on the breaker internally as the previous test, 160, 170 degrees. Let me cross check it with another one. 90 degrees on the bus bar, 92. 90 degrees, 93, 92. Now the battery cable is getting up there at 150. But now we're running on 16 minutes, so. I don't know what that is. I have to shut this thing down. The inverter's gonna blow up. It's freaking out. Could be our battery voltage is getting too low. These cells weren't charged that much. Okay, well, while these batteries charge up because they're quite low, inverter starts freaking out at 11.5 volts. I'm gonna go in and edit this video and try to figure out what the hell just happened. Why are we seeing such cool temps on these single studs? It's the same bus bars. Everything's the same. It's just different cells. They're both cattle cells, actually. They're both 280 amp hour cells from cattle. I just got them from different companies, so that's crazy. Either something's up with my test, or I'm gonna have to possibly retest the double studs. So yeah, I'll be back. Okay, so I got the double studs back on the bench, and one thing I did differently is I put some EVA tape in between the cells because I noticed the spacing was such that it was possibly crimping the insulation under the bus bar. I don't think it's a problem, but yeah, let's give it a go. Here we go. Alright, we'll be back in about 10 minutes. Okay, just doing a 5-minute check-in, and I can tell you already just by using this little tester, every terminal right now is at 106 on these 3 cells. But this last cell, 166 degrees on those, 130 degrees about on these terminals. I checked the voltage of the cell for voltage sag, and it's 3.03 volts. That's good. This one's at 3.09. So it's not the cell, it's not the sag, voltage sag on the cell. It's a little lower than the others, but that's still fine. Alright, we're pushing up on 8 minutes. And you can already see that one cell I can't see the temp from my screen. I mean, from where I'm looking. It looks like 192 at the hottest point. That is crazy. 125. 132. That's the one with the breaker, so it's going to be warmer. That one's pushing 140. Anyway, I'm going to stop the test, and then we're going to swap out this one cell and see if we can resolve this issue. I think I figured it out. I was going to change the cells out, and I said, let me try one thing, because it makes no sense that one cell is going to be lower than the rest. Take a look. Notice anything different, huh? Right there, bam, look at that. See those bolts? See those bolts? I used a standard bolt over the lock washer bolt. And so far, it's pretty good. Let's check the temps. Yeah, so I was feeling these, I'm like, you know, the heat seems to be coming right from the bolts themselves. But it's really hard to tell because it's just superheating the bus bar. But yeah, I can definitely feel the difference. Like, I can hold on to these. I cannot hold on to these. No bueno. Let's take a look. So now, you can see that stud over here, cell number 4, is running the coolest, actually. It's cooler than all the others. Check it out, you can't even see it on the heat profile. Look at that, beautiful. 101 degrees. We'll go over here. Look at that. 130 degrees. That's interesting because the actual head of the bolt is not very hot. So I think it's just creating a lot of resistance, and the heat's being generated right on the terminal stud of the cell. That's crazy. Okay, so I'm going to swap out all the bolts that have the lock washer and the washer for the standard bolts, and I'll be right back. Okay, so all the bolts have been swapped out for the standard bolts, the serrated head bolt. Serrated. Okay, I'll be back in 10 minutes. Okay guys, we're pulling up on 10 minutes, and I can tell this is already feeling really good. Starting on the far left over here, that's going to be warmer because of the cable and the connection there. But you can see the stud, 82 degrees. The actual stud is about 104 max. Move over to the next one here. Same thing, 100 degrees max. So much better than the other bolts. $100 on that one, less than 100 degrees. $100 on the terminal. 84 degrees on the bolts. So the studs are staying around 100 degrees, but the surface are around 80 to 85 degrees. And in the middle of the bus bar, 100 degrees. And that's at 12 minutes. Let's take a look at the breaker and cable. So per usual, the breaker internals are pretty hot, 160. Same temps we saw before, not surprised. But the contact terminal looks to be around 90 to 113, 120. And let's look at the cable. So of course near the connection it's going to be really hot. As you go down the cable, you're going to see it's cooler, 120, 130 max. The cable looks good to me. And these cell studs, these are really good. These are actually doing really well. Okay, let's talk about the components, specifically these bolts and why they may fail. I think the reason they're failing, they're not very magnetic, so they could be aluminum. I can't tell because I cannot take this washer off. They're machined on there in such a way I would have to cut it off. So I think only the washer is actually magnetic. So I'm not sure what these are made out of. So there's two reasons. It could be aluminum, and aluminum just sucks at conducting. The other reason is, if you notice, there's some play in there, right? On the bus bar. So what has to happen, you can see how that moves around like that? So what has to happen is the bolt at high current has to end up taking on some of the current. So the current has to actually flow through the bolt up into the head and then back down through these washers and the lock washer back into the bus bar. And that can create a lot of resistance as well. So those are the two reasons. This one, however, standard bolt, serrated bolt, I think it's zinc, very magnetic, and it's a solid piece, right? So the head is actually more broad, but I think mainly it's the material that the bolt is made out of is what the problem is. So that's a pretty solid connection there. So where else have we seen these style bolts? Well, we see these all the time on battery terminals. They use these even on the Yixiang box on the external battery terminals. These are the same thing, except they're M8. However, I think they use zinc bolts instead of whatever these mutant bolts are. So on these bolts we saw a minimum degree of 150 to 200 max, so that's definitely a fail. On the standard serrated bolts we saw an average temperature of around 100 degrees, definitely a pass. Okay, next up is the battery cable. What determines the ampacity in a battery cable, or any conductor for that matter? Well, the length of the cable, not so much. The cross section, how thick the cable is, what material the cable is made out of, the conductor inside, aluminum or copper. And also what's very important is the insulating jacket and what temperature is rated for. There's a 125 printed on here. I'm not sure if that's the temperature rating, but if it was, it would be probably in Celsius, so 125 degrees Celsius. The max temperature we saw on this battery cable was 130 degrees to 140 degrees. And mostly that temperature came from the circuit breaker heating up the cable on the terminal and propagating the heat down the cable. As far as the cable itself, 50 millimeters squared, I think this is definitely sufficient for 200 amps. Sure, you can bring it up to 70. It's not much more expensive for these companies to do. There's no reason they shouldn't do it, really. But 50 definitely is sufficient for 200 amps. Let's talk about the circuit breaker. This is a thermal breaker, so it does have to heat up in order to work. The heat is directly relational to the amps going through it. These breakers do not look at amps specifically. The more amps, the higher the heat, the faster it breaks. Typically you want an 80% duty cycle on your max continuous load. So for 200 amp BMS, max continuous load would be about 176 amps. So for a 220 amp breaker, that's too low. A minimum of 250 amps would be required for an 80% duty cycle at 200 amps. I think the contact terminals are just too small on this for 200 amps, and that's what's creating most of the heat. And internally we saw a lot of heat being generated inside the breaker itself. So I think this is insufficient. I give this a fail. As far as the shims are concerned, I don't see a reason for these. There's no good reason. Obviously in their design they have to have it in order to bridge the connection for the single lug cable. But if they use a double lug on both sides, this would not be a problem, and they can just get rid of these. There's no reason for these. It's just restricting the current. Although I didn't notice a huge difference in heat being generated. It's hard to tell because most of the heat is internalizing, being generated inside, and it's just propagating through. But just looking at the video, I could see the heat profile slightly better without these. But yeah, so I give these I don't know. We'll just say not needed. Okay, copper bus bars. Pass. These are great. Nothing wrong with them. Aluminum, however, we didn't have a chance to really properly test these. So in general, aluminum is a crappier conductor than copper. So yeah, you always have the choice. Definitely go copper over aluminum. So bus bars, a pass. Okay, the big question now. Single stud, single welded stud versus the double M6 stud. I didn't see much of a difference. I want to say that this ran slightly cooler, but really, I didn't really see much of a difference. So I think single studs are perfectly fine, and these are perfectly fine. So whatever you like. Well, that was a lot. I learned a lot. I hope you guys did. Here's the thing, though, with these 48-volt batteries, I don't know really who's using a single battery at 200 amps continuous. If you have an EV car and you're charging with 10,000 watts, for example, you're going to dump a 15 kilowatt hour battery in about an hour and 15 minutes, hour and 30 minutes. But that's no excuse. If the company is using 200 amp BMS, then the battery should be rated and should be able to handle a 200 amp continuous. But that's no way to treat your cells. So batteries work best when there's power in numbers, right? So if you have many batteries in parallel, you're distributing your load across all those batteries. Your cells will thank you for it. They'll last a lot longer. Each battery will have to bear less of the load. And that's why we do this testing.